Imagine a star much bigger than our sun, a colossal giant that dwarfs our solar system's centerpiece. This star is a giant, a behemoth in the cosmic ocean. It burns bright, fueled by nuclear fusion, a process that powers its intense luminosity. Deep within its core, it fuses hydrogen into helium, releasing enormous energy that radiates outward. But its life cycle is different from our sun's. Unlike our sun, which will become a red giant and then a white dwarf, this star has a more dramatic fate. This giant star doesn't just stop at helium. It continues to fuse heavier and heavier elements in its core. It fuses elements like carbon, oxygen, and even iron, each stage releasing energy and creating new elements. It creates carbon, oxygen, and even iron, building up layers of different elements within its core. But fusing iron doesn't release energy. Instead, it consumes energy, leading to a critical problem. It actually takes energy away, causing the star to lose its battle against gravity. This is a problem for the star. Without the outward pressure from fusion, the star can no longer support itself. Without energy pushing outwards, gravity takes over, pulling the star's material inward. The star's core collapses in on itself, a catastrophic implosion that happens in a matter of seconds. This collapse happens incredibly fast, faster than the blink of an eye. The outer layers of the star explode outward in a brilliant supernova, a cosmic fireworks display. What's left behind? Sometimes it's a black hole, a region of space where gravity is so strong that not even light can escape. Black holes are mysterious objects. They have a region of no return, called the event horizon. Imagine a giant invisible sphere around the black hole. Once you cross this sphere, you can never escape. Not even light can escape the pull of a black hole. That's why they appear black. At the very center of a black hole is the singularity. This is where things get really strange. The singularity is a point of infinite density. All the matter from the collapsed star is crammed into this tiny point. It's hard to imagine, but that's the power of a black hole. Falling into a black hole wouldn't be a pleasant experience. As you approach the event horizon, something strange would happen to time. From your perspective, time would seem to slow down. You would see the universe around you speed up. But from the outside, someone watching you would see something different. They would see you slow down as you get closer to the event horizon. You would appear to freeze in time, your image stretched and distorted. Eventually, you would fade away completely, swallowed by the darkness. Section 4. Death by black hole spaghettification versus firewall. So, what would happen to you if you fell into a black hole? It's a question that has fascinated scientists and science fiction enthusiasts alike for decades. Well, there are a couple of theories. One is called spaghettification. This theory is based on the immense gravitational forces at play. Imagine being stretched like spaghetti. Your body would be pulled apart atom by atom as you get closer to the black hole. Yeah, that's what would happen to your body. The gravitational pull is so strong that it would elongate you into a thin, noodle-like shape. The gravity of a black hole is much stronger at your feet than at your head. This difference in gravitational pull is what causes the stretching effect. You would be stretched and stretched until you were ripped apart. It's a gruesome but fascinating way to go. Another theory suggests that a firewall exists at the event horizon. This is a more recent and controversial idea in the world of physics. This firewall would incinerate anything that touches it instantly. Imagine a wall of fire that burns everything to a crisp in a fraction of a second. So you wouldn't even have time to be spaghettified. The moment you touch the event horizon, you'd be vaporized. You would be gone in a flash of energy. It's a quick, albeit terrifying, end to your journey into the black hole. Section 5. Black holes aren't forever. Hawking radiation and evaporation. Black holes seem invincible, but they aren't. Despite their immense gravitational pull and the fact that they can trap even light, black holes are not eternal. They have a finite lifespan. They actually evaporate over time. This process, though incredibly slow, leads to the gradual shrinking of the black hole. This surprising discovery was made by Stephen Hawking. It's called Hawking radiation. Hawking's groundbreaking work revealed that black holes emit radiation due to quantum effects near the event horizon. Empty space isn't truly empty. Even in the vacuum of space, there are virtual particles that appear and disappear constantly. It's filled with virtual particles that constantly pop in and out of existence. These particles are a fundamental aspect of quantum mechanics. Near the event horizon, one particle can fall into the black hole while the other escapes. This interaction is crucial to the process of Hawking radiation. The escaping particle becomes real, taking a tiny bit of energy from the black hole. Over time, this loss of energy causes the black hole to lose mass. This process is extremely slow. The rate of evaporation is so gradual that it takes an unfathomable amount of time for significant changes to occur. It takes a very, very long time for a black hole to evaporate completely, but it does happen. Over billions of years, the black hole will continue to shrink until it eventually vanishes. Eventually, even these cosmic giants disappear. The once mighty black hole will fade away, leaving behind only the faintest traces of its existence.